Topic03C, assembly language. So this is the second part of our two-part series on the instruction set. So the next instruction set I actually want to talk about is our arithmetic instructions. So we're actually able to perform many mathematical operations, and of course the basic ones that we have at our disposal are add and subtract and multiply and divide. We basically perform these instructions using an accumulator and some other operand, whether it comes from another accumulator or whether in fact it comes out of our memory. Depends on which sort of instruction you're using and which addressing mode that you're actually using to define where in fact it's coming from. So as I said, the primary operations that we have at our disposal on the HS12 are in fact add and subtract and multiply and divide, so the four primary operators. So adding and subtracting is primarily done with accumulator A, accumulator B and accumulator D. You can also do addition and subtraction with the X and Y index registers, but that's a little bit more a roundabout way and it's a bit beyond the scope of these lectures. But if you want to use those accumulators, then by all means look them up in the instruction set to see how they work. But I'm primarily going to focus on just the basics with accumulator A, B and D. So when it comes to addition and subtraction, we have the instructions yet again. The instruction mnemonic itself pretty much gives away exactly what the instruction does. So when it comes to accumulator A, we have add A, and then when for subtraction we have sub A. So it's the add and the sub that define the operation we're doing, and it's the letter on the end that effectively defines what accumulator we're doing it with. So we've got add B, sub B as well, and sub D, and add D as well. So we've got those 6 mnemonics which allow us to do addition and subtraction with our accumulators. So to give you an example of using these instructions, I've given you a simple example in blue and a slightly roundabout, more complex example in brown. So in the blue example, we simply load accumulator A with the decimal value of 32, and we simply add to accumulator A the value of 12. So therefore, accumulator A will in fact hold the result, which is 32 plus 12, which is in fact 44. So at the end of that instruction, add A instruction, accumulator A will in fact hold the decimal value of 44. In the second example, the brown example, I've given a slightly more roundabout way of using the same instruction. First of all, I've simply stored the value of 45 into the variable called data. So I've done this using a move B. I've then gone and loaded the index register with the location of data. So I haven't loaded index register X with data, but I have loaded it with the memory location where the variable data actually lives. I've then gone and stored the value of 12 into a variable called variable, and then I've simply loaded accumulator A with the data where X refers to. So X was pointing to my variable called data, so therefore I've now loaded accumulator A with the value of data, and then simply I've added to that value of data the contents of the variable called variable, which in this case is 12. So therefore in accumulator A I will now have the value of 45 plus 12, which is in fact 57. So accumulator A, is, after running all those instructions, accumulator A will in fact have the value of 57 in its registers. So that's all fine and dandy when you're just dealing with single bytes or single words, but what happens when we're doing multi-word or multi-byte numbers? So when we've got a number that's too big to hold in a 16-bit register, and we've primarily got, say, a 32-bit number to hold it, how do we add a 32-bit number together by doing two separate 16-bit additions? Well, when it comes to adding the lower 16 bits, we can simply add it using the standard add instructions. But when we need to add the most significant 16 bits, we need to take into account any carry that may have happened as a result of adding the least significant bytes together. So therefore we have a series of instructions which will actually do an add with the carry. So not only will it add the two numbers together, but it will also add in any value in the carry bit in the condition code register. So if the carry bit in the condition code register is set, then it will simply add 1 onto the summation. If the carry register so carry bit inside the condition code register, if that is actually 0, then of course it's plus 0. So this is good instructions for doing multi-word addition. And of course, you've got the same thing with subtraction. If you need to, say, if you subtract the bottom two bytes, and it's actually had to borrow from the most significant bytes, then in fact you can do a subtraction with borrow, and then it will take into account the borrow that you've borrowed from the most significant bytes. So to give you an example of this is a multi-word example. So first of all, we've got a number which consists of, it's simply a 16-bit number for simplicity. So the least significant bytes are 32 and 12. So we've simply added 32 and 12 together, and that will give us our value for our least significant byte. These are hexadecimal values of 32 and 12, so we've added them together, and that gives us our least significant byte value, the addition of those two. Then we've gone to add the most significant byte together, okay, which in this case is the 67 and 78. So simply when we add the 67 and 78 together, we need to take into account if a carry took place from the lower number, which in fact it didn't, but just in case it did take place, we need to, when we add the most significant byte together, we in fact need to add it with the carry as well. So therefore we simply load accumulator A with 67, and then we do an add ADCA, which is an add with carry accumulator A, and we simply add 78 to that, and therefore adding those two together plus the carry will generate our most significant byte. So there is an example of adding a 16-bit number together, but doing it with two separate 8-bit additions. In reality, if you're going to do this on our processor, you'd simply just use accumulator D and just simply add it as two 16-bit numbers. But here's an example of how you might deal with multi-word numbers. So if there were 16-bit numbers, there was a 32-bit number and there were two 16-bit components, then you'd do it the same sort of way, but you'd be using accumulator D instead of accumulator A. Okay, when it comes to using binary coded decimals, you remember that binary coded decimals use 4 bits to represent each one of the decimal digits. So inside those 4 bits, we can only in reality have a number between 0 and 9 because it's a decimal coded binary. So we use 4 bits to represent the digits between 0 and 9. Therefore, the value of 10 to 15 in those 4 bits is an invalid number. So therefore, if you're adding two binary coded decimals together and it produces a value in those 4 bits that's greater than 9, then that's actually an error has taken place. But one of the beauties of this processor is that when you do this addition and you get a number that's greater than 10, the H flag is actually set. So the H, or the half carry flag, is actually set to say that, hey, a number greater than 10 has resulted in those lower 4 bits, and therefore if you run the command called DAA, which is the decimal adjust command, it will actually add 6 to that number to force it to become a correctly encoded binary coded decimal. So there is a command called DAA that you can run to simply correct for any binary coded decimal addition that you may have done. Okay, and this works purely on the half carry flag. So as I said before, the half carry, when you run DAA, if the half carry flag is set, it adds 6 to it. If it's not set, then it leaves it well alone, because the number that resulted, or number that you got as a result of that addition, didn't in fact exceed 10 in those 4 bits. None of the 4 bits in that number actually exceeded 10, so it doesn't have to actually do any addition to correct the numbers. When it comes to dealing with numbers, there are situations where we need to change the sign of a number, so we need to actually negate a number. Okay, so you might have a positive number, you need to make it negative for some reason, so we have negate commands. Okay, these negation commands are not the same as a ones complement command. These negation commands actually do a twos complement on the number. So when you go neg, it simply operates a twos complement on that number to make a correct negative number. Okay, so when it comes to making negative numbers, we can do it on 8-bit or 16-bit numbers. So we have neg B and neg W to be able to work on 8 or 16-bit memory locations. We have neg A, neg B to be able to negate accumulator A and accumulator B. If you want to negate accumulator D, it is not using neg A and neg B. That will give you an incorrect number, but you can in fact negate accumulator D by simply subtracting 1 from accumulator D and then complementing accumulator A and accumulator B, which is the reverse of doing a twos complement. So there are ways around it. If the instruction doesn't actually provide it, it just takes a few more instructions to do it. And then of course we have the extended sign or sign extension command, which is useful if you do a transfer if you transfer a 8-bit number into a 16-bit register, effectively it's the 8-bit number will appear in the least significant byte of that number. If that number was in fact a negative number, then you automatically change the sign of it, because that negative number will sit in the lower 8 bits of that 16-bit register, but the top 8 bits of that 16-bit register will be 0, which sort of tells the processor that it's a positive number, because the MSB is not set. So if you transfer an 8-bit number to a 16-bit register, you effectively need to preserve the sign of that number. So if you transfer it, then generally you'll run the sex command, okay, which will do sign extension, which means it'll detect the MSB, so the most significant byte, in the 8th location of that 16-bit register, and then it will copy it up to the higher 8-bit. So it'll simply go to bit location 7. So if you assume the number is from bit 0 is the least significant bit 7 will be the most significant bit of that 8-bit number. We'll simply read bit 7, and it will simply echo bit 7 from all the way from bit 8 all the way up to bit 15. So it'll simply take that most significant bit in the lower 8-bit lower byte and simply echo it up to the higher byte and simply do sign extension. So I've given you an example here of simply doing a negation. So simply load accumulator A with the decimal number of 32. We do a neg A, which simply negates that, which makes it negative 32. Okay, so it simply does a 2's complement on that number to give you the negative value. One of the really useful commands on this processor, and it's probably one of the most unused commands, is the multiply command and the divide commands. Maybe because these instructions are fairly complex to use, but once you've got the hang of them, they're very easy and become second nature. So when it comes to doing multiplying numbers, we can multiply 8-bit or 16-bit numbers, okay, and these numbers can be signed or unsigned depending on what sort of instruction you use to do the operation. So when it comes to multiplying 8-bit numbers, we simply take the two numbers, we put one number in accumulator A, we put one number in accumulator B, then we issue the multiply command, which is mul, M-U-L, and the result of that multiplication will then in fact appear in the combined register accumulator D. So simply load one into A, one into B, run mult, and the result will be in D. So to give you an example, simply load accumulator A with 5, load accumulator B with 6. We simply run the mul command, and therefore D will have the value of 5 times 6, which in this case is 30. So that's a really good way of doing multiplication. But be aware, multiplication command is a very costly command. It will take about 8 to 10 instruction cycles to do it properly. So it's not a command you want to use a lot. If you're doing a multiplication of 2, 4, 8, or 16, something that's a power of 2, it's probably easier to just simply do left shifts instead of actually doing multiplications, because left shifts are a lot more computationally cheaper than doing multiplication. So it depends on what sort of numbers you're multiplying. If you know beforehand and it's a factor of 2, then simply do left shifts. If you don't know, then of course you're limited to using the multiply commands. Okay, so when it comes to multiplying 16-bit numbers, of course, if you multiply a 16-bit number by another 16-bit number, that product will be a 32-bit number. So you can see we can't all of a sudden start using just accumulator D. We're going to have to start using a few registers to get the multiplier to work properly. So when it comes to multiplying 16-bit numbers, the numbers that we want to multiply, we load 1 into accumulator D, and we load 1 into the Y index register. So the two numbers we'll multiply, one's in D, one's in Y. We issue the multiply command, which might be emul if it's unsigned, or emul-s if it's signed. So running one of those two commands will then do the multiplication, and the resulting value will then be made available in the combined register of YD. So the most significant 16 bits will be in Y. The least significant 16 bits will be in D. Okay, so it'll be a combined 32-bit register consisting of Y concatenated with D. So to give you an example of that, simply loaded a sign to number, so it's negative 250. I've loaded that into accumulator D. I've then loaded Y with the value of 6. I've simply then issued the emul_s command, which means the D is multiplied by Y and the sign bits are preserved. So therefore the resulting value is inside the combined register of Y and D, which is negative 250 by 6, which is in fact will be negative 1500. So negative 1500 will in fact be stored in Y and D. So if you looked inside those registers, the register Y would simply consist of ones, which would be the negative sign, simply because it's a negative number. The front of the number is padded with ones instead of zeros, and the actual value of negative 1500 will in fact be inside D. So if you know beforehand what sort of limit or ranges that you're dealing with these numbers, if you know the number is not going to be full 16-bit number, you know it's going to be, the product will be limited to only 16 bits, then you can pretty much neglect the Y, but it depends purely on the application, and it's always best to check the values before you start dropping registers. Okay, so we've looked at the various ways of doing multiplication. Of course, the flip side of multiplication is, of course, division. So when it comes to doing division, we can do division of 16 or 32-bit numbers. Okay, so when it comes to dividing 16-bit numbers, we simply load the number that we want to divide into accumulator D, and the number that we want to divide the number in accumulator D by we load into accumulator X. So effectively, it's going to be D divided by X. And then, of course, you issue the divide command, so it's either IDIV if it's unsigned, or IDIV_s if it's signed. So the S on the end specifies it's signed. If it doesn't have an S on the end, then it's assumed to be unsigned. So the mnemonics actually give it away. So it's an integer division, so I for integer, div for, of course, division, and then S whether it's signed or not. So it's simply going to be D divided by X, and of course the result will then be in X. So once you do D divided by X, the actual division value will be in X, and the remainder will be in D. So you end up with the remainder and the actual value in the remainder in X and D respectively. Okay. So to give you an example, we simply load accumulator D with the value of 32. We then load X with the value of 6. So this is going to be 32 divided by 6. We run the IDIV command, and therefore what we will get in accumulator X is the result of 5, because 32 divided by 6 does give you 5, not a clean number of 5, but because this is an integer processor, we have no floating point, so therefore it'll give you back the value of 5, and give us the remainder of 2. So X will contain the value of 5, which is the result, and D will contain the remainder of 2, which is our remainder, because 32 divided by 6 gives you 5, and 5 times 6 is 30, so therefore the remainder in this case is 2, therefore D will equal 2. So when it comes to dividing 32-bit numbers together, we simply load one of the numbers into Y and D. So we simply load the 32-bit number into the combined register of Y and D. Then we load the number we wanted to divide it by into X. So it's the same as before. The number we divide it by is an X, but in this case we've got a 32-bit number, so we load the most significant 16 bits into Y, the least significant 16 bits into D, and then we run either the EDIV or EDIV_s instruction depending on whether it's signed or unsigned. So if it's signed, we run EDIV_s. If it's unsigned, we simply run EDIV. So the E stands for extended, because it's not an integer value, it's a 32-bit number, so E stands for extended number. So to give you an example, load accumulator Y with 1, 2, 3, 4, and we load accumulator D with 0, 0, 3, 2. So that total number that we're dividing through by is a 32-bit number, which is 1, 2, 3, 4, 0, 0, 32. We load accumulator X with the value of 6, 6, 6, 6, so 4 sixes. So therefore, when we run the EDIV command, we're in fact dividing 1, 2, 3, 4, 0, 0, 3, 2 by 6666, and they're all in hexadecimal format, hence the dollars in front of the numbers. And then, of course, the resulting value that we'll get will be in Y. So we get, in Y we get 2D82, which is a resulting value, and in D we get a remainder of 0, so there is no remainder in this case, so D will be 0. So that's how we can divide a 32-bit number through by a 16-bit number. So not only can our arithmetic logic unit do arithmetic instructions, but it can also do logical instructions. So the logical instructions that we can do in this ALU is, in fact, we can do logical AND, logical OR, logical XOR, and we can do ones complement. So when it comes to doing accumulator A, we can do an AND with AND A, an OR with OR A, an XOR with EOR A, and a ones complement with COM A. So the names of those mnemonics sort of gives away what instruction is that we're doing. So we've got AND, we've got OR A, and we've got EOR A, and COM. Okay, so depending on which accumulator that you want to do that on, or whether you want to do it on memory, you just pick the appropriate instruction. So to give you a simple example, we simply load accumulator A with a decimal value of 23. We then AND accumulator A with the number 8. And of course the result will be 0 because the 4th bit is not actually set inside the number 23. So therefore, simply AND them together, you get a result of 0. The other thing we can do inside our accumulator is we can actually do data test instructions. So we can actually test the contents of accumulators or test the contents of memory and things like that. So we can actually do a test, and as a result of a test, it actually sets the various bits inside our condition code register. So I'll come back later on and talk about, when we talk about conditional branching commands, these actually rely very heavily on the bits in our condition code register to whether they branch or not. So we have these compare commands which enable us to set the various bits in the condition code register prior to doing some sort of branching command. Or if you say want to just check the contents of a particular variable or so forth. So we can test the bits in accumulator A, so we can simply go bit A and we can give it an operand, which is a mask to define which bits we want to check. We can do bitwise test in accumulator B. We can also compare accumulator A to accumulator B, so maybe you load a value into accumulator A, you load another value in accumulator B, and you want to compare whether they're equal or greater than or less than or whatever. We can also compare an accumulator A to memory, accumulator B to memory. We can compare accumulator D to memory using the CPD command. We can compare X to memory, compare Y to memory, and we can compare the stack pointer to memory. One thing you've got to be very aware of with these comparison commands is these comparison commands basically do a subtraction. So whatever the operand you give, it will subtract that from the value in the register that you're comparing with, and it will set the condition code register depending on whether that resulting value is plus or minus or 0. Okay, it does that subtraction in a temporary secondary register, so it doesn't actually affect the contents of the register that you're comparing against. So if you do a compare A, and it'll do an implied subtraction in a different register, set the condition code values, but the contents of accumulator A will remain unchanged. They'll remain as they were before. So it's not a destructive comparison. It does it in a secondary temporary register somewhere else inside the processor. So when it comes to data test commands, we can also do tests. So you can test for memory, test the memory location. So you can do a test, an operand. It also sets condition code registers as well. You can do a test A and test B and so forth. Simply tests if accumulator A is greater than or equal to 0 and so forth. So we've got a series of test commands that we can use also. So to give you a few of these examples of using data test instructions, we've got LDAA. So we simply load accumulator A with a value of 20. We do a test A, and what happens as a result of the test A is Z is 0, N is 0, H is 0, V is 0, and C is 0. So one thing you know about the number of 23 is that it's not 0. Okay, so it's not a 0 value, so therefore Z is not set. It is not a negative number. Okay, it's a positive number, so therefore n is not set. It hasn't been involved in an operation that recently caused a half carry to take place, so h is not set. We haven't tried to make a 2's complement number out of it, and it's been too big to actually make it, so therefore v is not set. And of course, we haven't just done an addition to cause a number greater than 8 bits to be created, so therefore the carry bit is not set. So it simply sets those bits inside the condition code register, and then later on we could actually do something else after that instruction, which may cause us to branch somewhere depending on what values of Z, N, H, V or C are set. We can also do the same sort of thing, so we can load accumulator A with 23. We can do a compare A of 23, and therefore it will set the condition code flags accordingly. So I've talked about the branching we've talked about the comparison instructions, and they usually go hand in hand with a conditional branch instruction of some kind. So normally you'll compare a register to a value and then simply do some change of program flow using a conditional branching instruction. So a program is very, very rarely sequential. Okay, there are many times when the program flow needs to change as a result of some event that's taken place. So whether you've just compared a register and you've checked, oh, that's greater than or less than 0, therefore we'll jump if it's greater than, or we'll continue in doing the code if it's less than, things like that. We'll simply split our code down 2 separate paths depending on some sort of value in some sort of register somewhere or some event that may have taken place. So we use our conditional branching instructions to change our program flow. So the operation of these instructions is directly controlled by the status of the N, V, H, C, and Z flags inside the condition code register. So that's why we use a compare before we use a branch. So therefore the compare will set these flags, and therefore we'll use a branch instruction that will branch depending on what sort of value is in those flags. So we can pick a certain branching command that reflects the sort of which flag we're really concerned about. Okay. So the flags in the condition code register is set depending on the previous instruction. So if it's a compare instruction, the compare instruction effectively set it, but they can also be set as a result of an add or a subtract or something like that. Any sort of instruction that we've used beforehand can in fact set the condition code register flag. So therefore, if you really want to branch depending on a comparison, then you have the comparison, then the branch. You don't have a push or a pull or anything else between your compare and your branching, because they can in fact change the status of the condition code register, which means your branch doesn't actually take place. So generally we'll have our compare and then our branch straight after it. So thanks to these conditional branching instructions, our processor now starts to work effectively like a computer instead of a simple sequential programmable calculator. So when it comes to our branching, we have 2 forms of branching commands. We have short branches, and the short branches are branches that are capable of jumping either 127 forward from the program counter or branching negative 128 back. So effectively, we have approximately a range of plus or minus 128 from the current program counter value. So these are our short branches, and they can only jump that short range from our current program counter value. So they use a relative operand. So the value that you simply give it will be a relative value, but when you're doing it in your assembler, you simply give it a label, and the assembler will then calculate what the relative value is back to the label that you've specified in your code. So assembler will actually do all the difficult stuff for you. If in fact you're jumping too far, it'll give you an error saying that the operand exceeds the size of the operand, which means you probably want to use a long branch, which we're going to talk about next. So when it comes to using short branches, we have signed or unsigned commands. So depending on that operator we're comparing with or we're checking against, if that operator is a signed value, so the numbers are stored in memory exactly the same way. It's the instructions that you use that define it to be either signed or unsigned. So if that number in a particular memory location is a signed number, then you need to use the signed branches. If you're using that number as an unsigned number, then you need to use unsigned branches. Okay, so when it comes to doing short branches, signed short branches, we can branch if less than, so we use a BLT command. So the way that this table is set up is I have basically what the instruction does, a branch if less than, I have the mnemonic, BLT, and its operand, which in this case is a label, and then a symbol on the end which sort of defines what sort of logical operator we're effectively using with that instruction. So we're going to branch of less than label, we can branch of greater than with the BGT label, we can branch of less than or equal to using the BLE, branch of greater than or equal to using the BGE, branch if an overflow occurred using BVS, branch if no overflow using BVC. Okay, so we've got those branching instructions for short signed branches. When it comes to unsigned, we have a different set of mnemonics when they're unsigned. So we have branch if equal, BEQ, branch if not equal, BNE, branch if minus, BMI, branch if plus, BPL, branch of carry set, BCS, branch of carry clear, BCC. Okay, so they're the unsigned branches that we can use. When it comes to using long branches, so the beauty of branches is that if you've written your assembly code and you've put a short branch in there and the assembler whinges and moans that says, oh, this operand can't be calculated, then you just simply stick an L in front of that short branch to make it a long branch. And therefore it can actually see anywhere inside our memory space. So when you change it from a short branch to a long branch, the operand actually goes from being an 8-bit relative value to being a 16-bit absolute value. Okay, so therefore it can simply branch anywhere inside our memory map. So you'll never have the case of a long branch never being able to work. So a long branch will always work. It's usually better to use the short branches first because they take up less space inside our program space, and they also take less time to run because you've got one less operand to load in. So short branches are generally the better way to start with, but then if you get an error or short branch doesn't work, then simply convert it to a long branch. So I've got this exactly the same thing we had with short branches. We have the same equivalent instruction with long branches. So with long branch we have branch of equal to, which is LBEQ, branch of not equal to, LBNE, and these are unsigned first. We have branch of plus, LBPL, branch of carry set, branch of carry clear. So we have exactly the same ones we had with short branches, but now they're just long version with an L in front of the mnemonic. And of course we have the signed as well, so we've got branch of less than, branch of greater than, branch of less than or equal to, branch of greater than or equal to, branch of overflow, branch of no overflow. So they're exactly the same instructions we had with the short branches, but now we have the long branch equivalent, which simply has an L in front of the instruction to say it's a long branch. So I've got an example here where we simply load accumulator A with value of 22 and we branch if not equal to loop. So we simply do a comparison. So if Z is equal to, so if the Z flag is equal to 0, which means it's not a 0 value, which means it's not equal to, it will simply branch back to loop. Okay, which will be some label somewhere in our code. So it'll be a label called loop in the first column somewhere that simply branches to. When it comes to writing any sort of program, I guess, there are always situations where we need to do iterative instructions. So we need to do a set of instructions a predefined number of times. So it may be predefined at compile times, that could be a hard-coded number, or it could be a variable that we need that then defines how many times we need to do a certain set of instructions. So when it comes to generating these loops, so to speak, we have a set of loop primitive instructions which make the whole, I guess, the whole structure of loops a lot easier to implement inside our processor. So when it comes to doing loop primitive instructions, we can use any one of our variables to hold this loop counter for us. So we can use accumulator A, accumulator B, accumulator D, X, Y, or even the stack pointer to hold our variable for our loop counter for us. So what we can then do is we can simply use one of the loop primitive instructions. So we've got decrement counter and branch if counter is not equal to 0. We can decrement counter and branch if counter equals 0. So we've got DBNE, which is basically the letters on the end are the same as the short branch command. So it's simply the same condition that we had with the short branch, but it's the D on the front that defines the decrement portion of that command. So a DBNE is a decrement, then branch if not equal. A DBEQ is a decrement branch if equal, which is one of the most commonly DBNE and DBEQ are the most commonly used loop primitives because you've got real control over exactly what happens with them. You've got the equivalent, which is increments as well. So you've got increment counter, branch if not equal, increment counter, branch if equal. You've got test counter and branch if counter equals 0, test counter and branch if counter, test counter and branch if counter not equal to 0, and you've got test counter and branch if counter equals 0. So you've got TBNE and TBEQ as well. So you've got these 6 loop primitive commands, which are very useful for setting up loops. So to give you an example here, we've got an iterative loop. So somewhere inside our, prior to running the DBNE, we would set up our accumulator A with the value that would define the number of iterations we actually want to do. So let's say we want to do 10 iterations of a chunk of code. We could simply then load accumulator A with a value of 10, have some other instructions that you want to do 10 times. So we have, LDAA hash 10 to load accumulator A, and then we'd have some instructions that we want to do 10 times, and then we'd have the DBNE command, and then we'd have a loop go back to the line under our load accumulator A. So therefore, we'd go back and simply run those instructions 10 times. So what happens with the DBNE command is it effectively, first of all, decrements. So it simply does A equals A minus 1, decrements it, and then it compares it to see if in fact it's equal to 0. So if it's not equal to 0, it goes back into the loop and simply runs that loop command, or runs from the loop label back down to the DBN again. Once it gets to the DBN, decrements it again. So it'll keep doing that, jumping back to that label loop and simply reiterating those instructions over and over and over and over and over and over again. When it gets to the case where, in this case, accumulator A is in fact 0, then it simply won't branch anymore. So therefore, it will just continue down to the next instruction after the DBNE. So it simply stopped doing that iterative loop. So DBNE are good instructions for doing loop structures. Okay, we also have unconditional branching and jump instructions. So these unconditional branchings is simply when we effectively want to jump somewhere. We don't, irrelevant of what operations taken place, we simply jump somewhere, or we simply branch somewhere else inside our code. So these are the simply unconditional, we simply branch irrelevant of what's taken place. So these are good for jumping around. So if you just simply need to jump to another chunk of code, or you simply want to jump to a subroutine, or you simply want to branch. Okay, so you've got these commands to simply jump. So JMP to jump, you've got JSR to simply jump to a subroutine. You've got BRA, which is branch always, so it's simply branching with no conditions. And we've got a branch to subroutine as well. One of the I guess the major differences between a jump to subroutine and a branch to subroutine is the jump to subroutine uses absolute addressing. The branch to subroutine uses relative addressing. Okay, so that's one of the that's the differences between those two. One thing to keep in mind with the jump to subroutine and the branch to subroutine is that when you run those commands, it effectively pushes a return value onto the stack. So it'll push a 16-bit return value. So it'll push the current program counter value onto the stack. It'll then simply set the program counter to wherever you want it to go. Okay, so in the case of JSR, it simply loads the operand into the program counter and then starts running that subroutine that you wanted it to run. When it gets to the end of that subroutine, it has to actually hit an RTS command, and the RTS command will simply pull the last 16 bits on that stack off and simply load them back into the program counter, which means as long as you haven't tampered with that stack inside that subroutine, effectively your program will be back where it was before it ran that JSR. So it will simply be pointing to the next instruction under the JSR, and it will continue on to your code. So a JSR has to be matched with an RTS, otherwise things just go haywire, they don't work. Okay, so keep that in mind when using a JSR inside the subroutine that you're jumping to. You need to have an RTS inside that, but we'll talk about that a bit more in detail later on. So to give you an example of an unconditional branch, we've used here the loop BRA loop, okay, which effectively causes the code to, when it gets down to this line, simply stop and spin on itself. So it'll simply keep branching back to itself, which means the program will in fact halt. And you'll notice that this is an instruction that we use inside a lot of our assembly codes, because if we don't stop the program from running, it'll simply start running whatever code's sitting in the memory after the code we've uploaded. So if we upload a chunk of code, we only want it to run that code. So therefore, the last line of our program, we get it to spin on the spot like this, because if we don't get it to stop and spin on the spot like this, it will simply go and run whatever random data is in our memory space after the program we've uploaded, which will give us some undesired results. So we always try and just stop our code, or we have it in an infinite loop that never exits. But if you don't have an infinite loop, then you put an infinite loop on the end here using this sort of structure, you get it to branch back onto itself. Okay, when it comes to doing the condition code registers, we can actually specifically set the bits inside our condition code register, and these are generally done using two commands. These are the OR condition code command, which allows us to set bits, and the AND condition code, which allows us to clear bits. So when you're setting bits using the OR-CC, you effectively give it a bit mask to define which bit you want to set. Okay. When you want to clear the condition code register, you use the AND-CC command, and you give it the negation of the bit you actually want to clear. So you simply, in this example here, we've got OR-CC 1000000, so we've got the most significant bit set to 1, which means that it will actually set the stop bit. Okay. With the AND-CC, we've simply given it AND-CC 0, 1, 1, 1, 1, 1, 1. So the most significant bit in this case is 0. Therefore, this will actually clear the stop bit inside the condition code register. So using those two commands, we can actually set or clear the various bits of the condition code register. So when it comes to using the condition code register, there is one really important bit that actually lives inside our condition code register. It is the I bit, and the I bit is effectively what we use to enable or disable our interrupt subsystem. So if we're using our interrupts, we need to ensure they're turned on. If we're not using them, then we need to make sure they're turned off. By default, they're generally off, so if you don't touch them, they'll stay off. If you need to use them, then you obviously need to turn them on. Turning them on at the appropriate time is also important, but we'll talk about that later. When it comes to turning on the interrupts, it effectively means we need to clear that I bit. We need to set that I bit to be 0 to turn them on. So therefore we can use the CLI command, which will actually clear the I bit. When it comes to turning off the maskable interrupt subsystem, we use the SEI command. So SEI means set I bit in the condition code register. The CLI and SEI commands aren't directly supported inside the processor, but the assembler will actually make the mapping for us from the CLI to the AND-CC command or the SEI to the OR-CC command. So it'll actually do that automatic mapping from the mnemonic CLI or SEI into the actual equivalent AND-C or OR-CC commands that are actually required to do that properly. There's one other really important instruction that we use, and it's the NOP instruction. Okay, the NOP instruction is a good command for doing nothing, does absolutely nothing, doesn't change anything, doesn't change the status of the condition code register, does absolutely nothing. It is what we call the no operation instruction. But one thing that it does do is it takes exactly one clock cycle to do nothing. So the no operation instruction is really good if you need to delay one other instruction by one instruction cycle. So if you've got to say talk to a particular device and you've got to just have one line go high and you've got to wait a certain number of clock cycles before you make that line go low, then you can use no ops to enforce a little bit of a delay inside your code. So no ops won't do anything apart from take one clock cycle to do nothing. So it's really good for doing delays. It's priceless command. If it didn't have it, lots of things wouldn't work. Okay, so of talking in these two lecture topics, 3B and 3C, I haven't covered all the instructions, but I've covered the most important ones. So I recommend you have a look at the full assembly instruction set to see all the possible instructions that are available, but hopefully I've given you enough insight into the various instructions to enable you to use all the other instructions that are at your disposal. So should you require any further assistance, then please do not hesitate to ask your demonstrator, post a question on the forum, email me the convener, or make an appointment to see me, knock on my door, come and, hound me after the lectures, hound me after the toots, but whatever means you choose, please ensure that your questions get answered.